another podcast. It's still in chapter two. So looking at structure, and just the big picture of how things come together. We're going to do Fischer projections today. And what that's going to entail is your first challenge when it comes to three-dimensional projections. And so we looked briefly at actual molecular structure, looking at like tetrahedral centers, looking at sp2 and sp hybridized carbons and how those become planar or linear. And so that's really critical. But because biology uses a lot of Fischer projections, that's the most common spot you'll see it, especially with sugars and amino acids. It becomes imperative that we know how to draw things different ways. And so what you're going to learn is, in general, if I have a molecule, let's say something as simple as ethane. So I'll draw it out. Ethane, ethane is two carbons. Not drawn perfectly, but I get the basic gist here. At each carbon, there are four things attached. This represents in the plane and going up. This is straight across that bond. This is down. This wedge, I'm going to color it in, represents an H coming out of the plane. This represents H coming out of the plane. This is H going back in. This is H going back in. Okay, now what I'm going to say is a side view. What we're going to learn, and if you ever took a drafting class, it's that things look different from your perspective. So we have a side view, but we could also, if we want to get a top view and a front view. All projections are, so we're going to learn about something called Fischer projections today, which are top projections. And then down the road, we're going to learn something called a Newman projection, which is a head-on view. And so depending on which way you look at a cube, it's going to be the same. But if that cube has a hole in one of the sides, then from one perspective, you'll see the hole, but other two perspectives will be hidden. And so it's not, I guess, a perfect system, but you need all three views to see something. So a Fischer projection will be looking from the top. And so it's always important to draw an eye and look at it accordingly. That's going to be an eyebrow. Here's your eye. A few things, though, is like anything, we have to make a few rules about how we structurally lined everything. So I'm going to erase this. I'm going to start into Fischer projection, pointing out that it's just a top view. So line your eye above a compound. So this is similar to what I just drew, except I only want to focus on one tetrahedral center. Okay, a few rules about drawing Fischer projections. When you look down on it, you want all the carbons to stick up like this. So, for instance, this molecule, simple enough because there's one central carbon with two groups coming off it, so it's easy to see. But if I had two carbons in central orientation, so let's say I had something like this, then again, it's important to draw the central carbons in an up fashion, meaning they have to point towards your eye. If you do that, you'll have something sticking out and something going in, something sticking out, and something going in on every carbon that sticks out. Okay, so point up or carbon up in the middle is important. So I'm going to go ahead and erase what I've drawn and focus on this. Which way you put your eyebrow is honestly arbitrary. So I'm going to put it this way. I'm always going to have my eyebrow on this side, my eye looking this way. And so this is going to require some visualization. And model kits help a little bit. Your fingers actually work really, really well. So if you put four digits out, so just fold your pinky down and have a thumb, index finger, ring finger, and middle finger out and about. And depending on which way you rotate it, you can see the front of your fingers, back of your fingers. So just get used to that situation. And then if you look at it, try to see like your palm and have everything sticking up, or the back of your hand and see everything sticking down. Just practice with how you see things. And in your mind, once you look at your hand rotating around, see if you can visualize it. If you can, great. It's just, that's more training than anything else. It's not going to make a big difference here other than just get used to what things do when they rotate around. So in this case, if I'm looking at this molecule, this carbon is pointing up, this OH is coming up, but coming out of the page or out of the plane of your screen. This H is going up, but back into the plane of the screen, so it's going end up behind it. These lines represent perfectly in the plane. So this bond here in the plane, this bond here is in the plane. So what you're going to do is you're going to squish this thing into a T. You're going to take it and compress everything down. So if you did that, stomp on it, like really squish that thing. If you push this down, if this H came down to here, that O comes down to here, it would look kind of like this. The CH3 and the OCH3 would still be in the plane, but they'd be squished. And then the H is going back, the OH is coming out. So if I could squish this from 3 dimensions into 2 dimensions, it looked like something like this. And my eye is still in the same position. My eye is still looking down on it, but now the squish version. And what we're going to do is we're just going to now ignore the dash and wedge and just know that nothing is going, let's say, in or out per se. We smashed it. Just make T-like. So we're going to get rid of the central carbon. And we're just going to draw this. So just like we do with line bond, we get rid of carbons because we just assume that's an intersection. And then we have to decide what is the top. So if your eyebrow is here, your eyebrow is top, if you will, it's above your eye. So we define this as the top. So I'm going to label this as this is the one that's top. Complete opposite side of the top will be the bottom. And then if you're looking at this carefully, if I were to go from top and pass through the H, I'd have to pass on the right side of that line. So I'm going to draw this H on the right side. And then if I pass from this top CH3 on the left side, pass through here to the bottom, that makes this the left side. So you have taken a 3-dimensional structure you know and visualize well and stomped it. You look at it from the top. So rotate so that your eyebrow is up there. So notice that this was the top. Let me just make sure that was the top. This was the bottom. This was the left. And this was the right. These will take a little time to get used to, like everything. But once you do a few of them, trust that they'll get better and better and better each time. So I think a really good question to always ask is, why are we doing this? Why should I do this? Well, main thing is, in biology, you have so many sugars and so many structures, and it takes so much time if you were to draw out 3-dimensional accuracy at every single carbon, every single position. It becomes time consuming. And honestly, it gets sort of redundant. Certain sugars have similar shapes. And so what they do is they just draw a standard Fischer projection of a sugar, and they expect that you get used to that and you can translate it as needed. So it's just for ease and convenience, just a different way to draw it real quickly. So you probably, don't know for sure, but you probably have seen this in your bio travels. This represents a carbon chain. They might draw a CH2OH at the bottom. They may have drawn an aldehyde carbon at the top. And then these branches coming off. These represent carbon, 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 carbon. Make the last one a substituent, draw on the actual carbon itself for whatever reason. And then you put the OHs here. OH left, OH right. I'm sorry, I said that totally backwards. OH right, OH left, OH right, and OH right. On this side, we put an H, and an H, and an H, and an H. And you have just drawn the Fischer projection of what's known as D-glucose, a very common sugar we break down. So it's easier to just recognize this structure and draw it over and over and over instead of trying to get 3-dimensional accuracy. And quite honestly, some people will be challenged in drawing the 3-dimensional accuracy, so it sort of saves them a little bit of time. So it's for convenience of drawing. And in chemistry, we don't use them that often, but in bio, you'll use them quite frequently. So that is my glucose residue. And in office hours, I may show you a cool trick to memorize glucose. But for now, I'll go ahead and move on. So Fischer projections, I want to, again, place my eye. I'm going to always have my eye here. I like to put the eyebrow on this side. It doesn't matter which side you put it on. It just doesn't, but we're going to do this. So I'm going to start with this structure right here. So I have this compound that's 1 carbon, 2, 3, 4, 5 carbons in the chain, OH on carbon 1, OH on carbon 2, OH on carbon 3, along with a CH3, OH on carbon 4, along with the bromine, and then a fifth carbon. And I numbered as such because your number one should go on the priority with the highest oxidized functional group, which in this case, alcohol beats an alkane. But if you recall, all your middle carbons have to be pointed up. So this one's pointed up, so that's fine. This carbon's pointed up, so that's fine, but this one is not. This is really hard to visualize, but I need to rotate this carbon from bottom to top, which means it's going to end up here. So that's a 180-degree rotation. So this CH3, if it's down and in front, it's going to rotate to here, where it ends up and in back. And this OH, it's starting in back and down. So 180 is not quite going to get it to the plane. So it's going to end up and in front. So I have rotated the structure itself into the backbone that I need. So carbons on the end, the terminal carbons are always low points, and then everything has to be higher. Every single carbon you connect to has to be higher and higher. So these are going to be the middle carbons. These are the ones going to make up those crosses, those T's in the structure. Okay, squishing time. So line it the right way, number one. And number two, squish it. So when I squish it, this is going to get stomped into this CH3 being here. This OH, if it's out, it's going to be on the left. This BR is in, so it's going to be on the right. This OH on the third carbon is going to be out. Timeout. Did not want to do that color. This one's going to be out. So it's going to be left. The CH3 on carbon 3 is going to be in. So it's going to be right. And then the H on carbon number 2 is out. So it's left. And then finally, OH is in. So it's right. What I've drawn is wedges here, and I want to emphasize when I squish it, they're still coming up. They're like bow ties. So this becomes kind of important in translating the other way, which is why I put this in. Instead of straight lines across, I'm going to turn in straight lines in the end. But before I do that, I want to emphasize the green here to match the green over here. So here are my green carbons. 1, 2, 3, 4, 5. Although nomenclature-wise, this is carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. And I'm just counting. So 5 over there become these 5 here. So that's that carbon, that carbon, that carbon, that carbon, and that carbon. So hopefully those become clear. This OH, again, is out. This OH is out, and this OH is out. So those become the ones on the left. And then the BR going into the page, the CH3 going into the page, the OH going into the page. There, if you're looking down on it and you put your hands out right side and left side, your right hand would go in. So in ends up on the right. So your BR, your C, and your OH become your BR on the right, your CH3 on the right, and your OH on the right. So hopefully this translation here becomes kind of clear. I mean, reflexive is the word I'm fishing for. That you do enough of these, you just sort of by reflex recognize things on the out will go left, thing on the in will go right. And then anything on the backbone makes up that straight line. This structure isn't quite right, so we need to rotate it. So we're going to rotate this up, rotate this down. So again, my eyebrow is up here, meaning I've arbitrarily decided this is the top of the molecule. I could have started with this end. So again, I want you to just know you can draw these things from either end. You decide which is top. For sugars, they typically start with carbon 1 being the top. So if I want to follow bio convention, I should have made this the top, spun it around. But guess what? In the very end, I can spin it around and I've solved my problem. So it really doesn't matter which way you do it from, you can draw it different later. Okay, you do not actually have the bow ties on here. I do want to emphasize, though, this is kind of convenient. Fischer, the person who came up with this, the chemist, um, pretty much every picture you ever see him in any textbook, once upon a time in let's say my college life, every textbook had pictures of these professors. I'm not sure what their motivation was, but we'd see these people wearing bow ties and think, yeah, that's who I want to be. I'm not sure if that's what it was, but it was something. But Fischer, always famous for wearing a bow tie, every picture. So it's probably why he did the bow tie look. He liked it. So that's coming out here, that's coming out here, this is coming out, this is coming out, this is coming out, this one's coming out. If you were to look at it in 3 dimensions, you're going to do a top view. But for Fischer projections, we just know that to be true, but we don't actually draw them. We just draw, or we don't draw the bow ties, we just draw the lines. And again, if I were to rotate this to the top and this to the bottom, anything on the left now becomes the right, anything on the right now becomes the left. Just like if I make this the top, coming out would be the left, but if I make this the top, going in would be the left. So it doesn't really matter how I start this one, doesn't really matter how I finish this one, as long as they match. If you need to rotate, change your perspective, you just rotate. Okay, these are challenging. It is worth your time to go slow and try this again if needed. Okay, so Fischer projections, I'll throw them at you this semester a little bit. Professor Santos, again, we're writing questions together, so you also get some of hers. We'll throw these at you, but you really are going to have to master this for bio. So there's certain parts of 311 you'll cover it, and then certainly biochemistry, you'll have to know it. The other thing I want to take advantage of at this point, before we get into the more hardcore crux of actual electron-based chemistry, is functional groups. So this is kind of the last pile of structural information to memorize, but you have to know a bunch of functional groups. So a functional group is any group that has a certain constant bond connectivity and a reactivity associated with it. So a specific attachment atoms that show characteristic chemical reactivity. So this is a much better way to word it. So for instance, we mentioned an OH before. So this OH group is an alcohol. So this is 1, 2, 3, 4 carbons with an alcohol. So I think we did this as one of our examples earlier. This is 1 butanol. And it reacts with SOCl2. So SOCl2, and I'm just going to draw arrows just to get a taste of what we're going to do in the future. But electrons, mentioned before, go from minus to plus. This is a delta minus because carbon is more electronegative. Oxygen's more electronegative than carbon. So you get a delta plus and a delta minus. And then oxygen's more electronegative than sulfur. So delta minus on the O, delta plus on the S. So the S will have a delta plus. Minus finds plus. So this is the first of many arrow drawings we're going to do. So if those electrons go here, now I have too many bonds. So those have to go up there. And I'm going to leave it like this. This is not a completed pathway, not a completed mechanism, but it is showing the basic gist of how an electron is going to flow. Two-headed arrow represents 2 electrons. One-headed arrow represents 1 electron. This represents my terrible artistic skills. When it's all said and done, those electrons kick in, the Cl is going to come off, and when it comes off, it's going to actually come in and substitute here. So a lot's going to go on, but in the end, this is just a first step. This is not a reaction, but I just want to, again, emphasize. This OH is a nucleophile. It attacks sulfur in this case, forms an alkyl chloride. So this is now 1-butyl chloride or 1-chlorobutane. Both. I'm gonna say either of those are fine. So N-butyl chloride actually means N normal chain or 1-chlorobutane, sulfur dioxide, and HCl. So it ends up, if I change the carbon chain to now be 2-methyl, 1-propanol, meaning I no longer have a 4-carbon chain, I have a 3-carbon chain with an extra carbon off the side. Prop meaning 3 carbons long. Notice it does the same thing. Still puts a Cl in the same spot, SO2 and HCl at the end. And then perfect, I happen to overlap right where it's drawn. Sorry about that. But this OH puts a Cl there. So you get the same reactivity over and over and over. And so the moral to the story is rather than saying this IUPAC name over and over and over, we can say a long chain primary alcohol, a branched alcohol, a cyclic conjugated alcohol. These words will make sense down the road, but the key thing, alcohol, 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 an OH on a carbon, OH on a carbon, OH on a carbon, without any other bonds to non-hydrogen, non-carbon atoms on this one. So this carbon has just carbon and H's and an OH. Carbon here has H's, carbon, and an OH. This carbon here has carbon, H and back, and an OH. So this would be known as an alcohol functional group. So in general, I'm going to tell you that an alcohol, ROH, is going to form alkyl chloride, SO2, and HCl when you react with SOCl2. So alcohols can undergo this reaction. So it's a so-called functional group. There are tons and tons of functional groups in OChem. We are going to just address a small portion of this semester. That portion is going to get bigger and bigger and bigger as we go through it. But I want to start with a series of different functional groups. This is purely for memorization. So here are a ton of words, ta-da, and spectacular introduction of a bunch of structures. So our job is going to be to take these names, 16 of them, and match them to these 16 structures. So easiest one, the one we just did, is this group right here is an OH on a carbon that just has carbons and H. So we already learned before that was an alcohol. That one's kind of a freebie. Okay, so other groups we have to know. So now we have 15 matches to do. When I move over one, instead of an S, or instead of an O, it's an S. If you recall, S is right below O in the periodic table, so they actually are kind of similar. And if you had to memorize amino acids for any of your classes, you'll know that the side chain of serine is an OH, whereas the side chain of cysteine is an SH, but everything else is identical between the two. So they have similar properties. Alcohol, this is known as a thiol. Okay, of course, I just went through the wrong one, so sorry about that. This one here, go in that direction. Carbonyl, C double bond O, attached to whatever is here, so it's a carbon. But the key thing here is a nitrogen. So anytime you have a carbonyl, C double bond O, and an NH2, it is an amide. Now, if we wanted to, we could make this an N with an H and another R group. It would still be an amide. In biochem, you'll also learn that when you have this linkage between two amino acids, it's known as a peptide. That's specific when the amide bond exists between two amino acids. So you have an amide. Okay. Am should give you some hint that there's a nitrogen. Ammonia, NH3. Ammonium, NH4 plus. Amide, N. So for this structure, look for the am, and lo and behold, have one right there. So this is amine. So let's see what's changed. O, N, S. Okay. So I already told you this is the thiol, so I kind of messed that one up, went out of sequence. This one then, I know it's a sulfur, so I'm going to take some hint. I know a thiol is up here. Ether, ester, ketone, carboxylic acid, alkene, aldehyde, anhydride, so forth. But I get to sulf. So more specifically, it's an alkyl sulfide because it's alkyl groups on it. But a sulfide is a sulfur with two things attached. So in this case, alkyl sulfide. This one I'm going to did already, toss it up. This carbonyl, so C double bond O is known as a carbonyl. That's a general term, not a specific functional group, but a generic term. This carbonyl can come, as we see, with an N. It can come with an R group, come with an H, and it can come with a Cl. So this structure right here ends up, when it's a carbonyl, instead of calling it an alkyl, when there's just all saturated carbons, We have a carbonyl, we call it an acyl. So I want to fish for this ether. Oh, there we go. Acyl, chlorine's a halide. So technically, this is an acyl chloride, but generically, I'm going to call it an acyl halide. But again, if you want to call it an acyl chloride, that's fine as well. That's a little more specific. This carbonyl, when it's just with two carbons on there, we call it a ketone. Can't believe I just jumped. I didn't mean to bump in that one. But this is a ketone, and when it's an H, it's an aldehyde. So am for amine, halide for this, but when there's just R groups, we have its own names of ketone and aldehyde. Okay, I apologize. I did not mean to bump and have the next one pop up, but moving to the next one, we have an alkene. So when we have a carbon double bonded to another carbon, it's called an alkene. Going one step up, when it's three bonds, we call an alkyne. So that's going to be there. Okay, trying to parallel. When sulfur, we call it sulfide. So this I thought should be an oxide. I don't see oxide anywhere to be seen. So our nomenclature rules don't seem very consistent. This is an ether. Ethers are highly inert because they don't react very much. We use them as solvents. Okay, this one had an halide, but it was an acyl halide because it was a carbonyl. In this case, everything is an alkane. So instead of an acyl halide, it's an alkyl halide. This one again mentioned when it's two R groups, it's a ketone. When it's an R group and in hydrogen, it's an aldehyde. So my ketone is going to come up there. This we're getting way ahead of ourselves, but if you have alternating single, double, single, double, single, double in a six-member ring, it adds an inexplicably large amount of stability, and it has to do with how the orbitals interact with one another, how electrons fill the orbitals. But it's a whole theory that we'll cover later on this semester called aromaticity. So this is what's known as an aromatic ring, meaning it's one that has 6 pi electrons, 1, 2 for double bond, 1, 2 for that double bond, 1, 2. So 6 in a ring that's completely alternated, single, double, single, double, single, double, called conjugated. Mentioned this one already. We have an alkene here. This is an alkyne. 4 to go, and I already know that the aldehyde is here, so I have a few to consider. You hopefully remember carboxylic acids from earlier. We talked about fatty acids. So fatty acids have this carboxylic acid group, so that's a carboxylic acid. This is an aldehyde, making this one either an anhydride or an ester. And it ends up, it is an ester. This one, for whatever reason, becomes a tough one for a lot of people to remember. So I want you to go look at those two and go, ooh, it's ester. I get so excited. So, ooh, it's ester. Ester is the one that has 2 O's and all the rest being carbon and hydrogens. Carboxylic acids are like an ester, but instead of the carboxyl group being attached to an OH, it's to an O with an alkyl group. Okay, next one, aldehyde, carboxylic acid. This is one of those I think you know already. Only one left, anhydride. It gets a name for the following reason. This is going to be one of the shortcuts that we'll do this semester. But if I were to cleave this bond right here, I could add water, OH and H, and result in this structure. So going backwards, if I got rid of this water and connected those bonds, I get the molecule I had before. So if I take 2 carboxylic acids and I remove OH from one and H from the other, so I remove water, it's now missing water. So instead of being with water, it's without water. It's anhydride, missing water. You're getting this functional group here. So let me go ahead and erase what I've drawn so you can see it more clearly. But this is essentially a carboxylic acid and carboxylic acid came together and lost OH from one and H from the other, lost water. It's an anhydride. The absolute positive ones you have to know now. You'll be testing on them soon. Alcohol, because we've seen so many. Ether, because it's going to be a common solvent. You'll deal with it in lab a lot. Alkenes, an entire chapter dedicated to them in this class. Alkyl halides, because of whom our nomenclature, ketones and aldehydes and esters, because carbonyls become reactive. It's one of the chapters we'll do. Carboxylic acids, because you have them from, I guess, other material, bio, and alkynes. The rest, they're fair game for testing you. Oh, I'm sorry, also amines. These are ones that are common we're going to deal with a lot this semester. But I also am expecting you to know every other one of these when we do quizzes, nomenclature exams. So these 16 functional groups are a starting point. We will add more as we go, but these 16 you have to know, and you have to be able to recognize and work with chemical reactions involving these 10. And then as we get into it, later in the semester, this one will pop in, the anhydride. Aromatic will pop in as a just a notable stability feature. The sulfur molecules, when we do substitution, this one will become an important one. As a nucleophile, this will be a product. And then amide and alkyl halide, not sure how much they'll pop up, but or acyl halide, excuse me, but absolutely important to know those functional groups going forward. So big thing, this is one of those lectures you might have to watch the Fischer projection part again. Just do it really slow and methodically the first time. If you have models, take the model and try to squish it down and see what it forms. And that's your Fischer projection. But good luck with this. And I will see you at the next podcast. Have a good day.